Hello, everyone. Our team worked on project number 43, motorcycle helmet test apparatus, sponsored by 60 Helmets. Our team members are Bula, Alejandro Bustos, Heriberto Cruz, Pablo Lara, and myself, Randeep Singh. Our advisor is Dr. David Raymond, and our liaison is Robert Reisinger of 60 Helmets. Here's our agenda, and I will begin discussing background and project scope. So the Department of Transportation, the Snell Foundation, and the Consumer Product Safety Commission are three organizations that provide testing protocols for linear impact energy tests. Figure A shows a helmet drop tower that complies to Snell standards. Some of these standards include the guiding system, which you see here on the figure, which delivers a controlled impact onto the test anvil. Another would be the shape of the test anvil itself, which in this figure is shown to be hemispherical. Current protocols do not account for impacts that are induced by rotational accelerations. However, biomechanics research has shown that there is a strong correlation between concussions and rotational head dynamics. This is due to the shear forces that are generated when the brain undergoes a rotational acceleration. These shear forces allow the brain tissue to be more easily deformed. Many helmet manufacturers have developed their own rotational impact testing methods, while some have implemented designs within the helmet itself to mitigate the rotational dynamics. One such company is 60 Helmets, our sponsor, which have patented a technology that they call omnidirectional suspension. And here we have a short clip to demonstrate how that works. So in this clip, the helmet is undergoing rotation, and what you see there are elastomeric isolation dampers that are equipped along the liner of the helmet. These help to isolate the impact energy and reduce the energy that's transferred to the brain from rotational impacts. In addition to that, we have two rotational impact methods that are employed by various manufacturers. The first of which is something that we're referring to as the free head drop. So in this clip, the helmet is simply dropped onto an angled impactor, which induces a rotation on the helmet. The second of which is something that we refer to as the head neck pendulum. In this clip, an angled anvil is in constrained vertical motion, and it is dropped upon a helmet, which is mounted on a head and neck assembly, which rotates the apparatus and makes it swing just as a pendulum would. The scope of our project is to design and build a multi-purpose drop test tower, which incorporates both linear and rotational testing capabilities, and that will meet structural integrity and our functional requirements. In this image, we have distinguished a schematic between the linear and rotational accelerations on the brain. Now I will hand it over to Vu, who's going to talk about our table of requirements.
All right, thank you, Randeep. So as requested by our team's liaison, the functional performance requirements and the method of verification for the requirements of the project is listed in the table shown in this slide. So the first requirement is to have the head and neck fixture to be able to rotate about Z and X axis, where Alejandro will explain further in the next slides. The drop shuttle for both testing methods have to reach 8.5 meters per second as required impact velocity. The design must have the repeatability of impact speed within 5% of theoretical value. The design must also have to be able to perform various testing purposes, which is having the impact points offset from the center of gravity. The last requirement is to have the different geometry replaceable angle anvil, such as a flat surface, 30 and 45 degrees angle. And then that will conclude our design requirement. And in the next slide, Alejandro will talk about the our final design.
All right, so the final design is broken down into three subsystems. The subsystems being the frame and arm, drop shuttle, and shuttle operation subsystem. The frame and arm subsystem consists of the structural frame, a hybrid 3 head and neck adapter, arm stopper, and arm connection. For the drop shuttle subsystem, this consists of drop ring, angled anvil, guiding rail, and sturdy anvil. And finally, for the shuttle operation subsystem, will have the lifting mechanism, releasing mechanism, and stopping mechanism. The figure to the right shows the overall design of the dual-purpose drop tower. We will go more into detail of each subsystem in subsequent slides. I'll begin by going into the frame and arm subsystem. So the first component of the frame and arm subsystem is the structural frame. So the purpose of the structural frame is to hold the arm and allow rotation without causing any disturbance to the drop tower upon impact. It was designed to easily be disassembled, and it contains 2 main members and 4 cross members. The main members are the vertical members, and the cross members are the horizontal members that connect the 2 horizontal members. The main members will be welded together, and the cross members will be bolted on using bolts, plates, and nuts, as shown in figure A. So all these components are made of 3 by 4 inch steel tube. And these will all be, as I mentioned, will be mounted using the bolts and the plate and the brackets. The whole assembly will then be mounted onto the ground using bolts and the welded on tabs located at the bottom. And finally, at the top of the frame, there is a couple weld on tabs that will prevent the arm shaft from rotating and translating. This is shown in figure B. Randeep will go more deep into the arm shaft in later slides. So now going into the next component of the frame and arm subassembly, we have the hybrid 3 head and neck adapter. The hybrid 3 head and neck adapter is designed to allow the operator to position and orient the helmet in different sets depending on the test that's being performed. Another feature of the design is to maintain constant horizontal distance from the drop anvil or impactor. This is done by having the bolt pattern along the arm, which will allow the adapter to slide as the angle changes, keeping the position of the helmet constant from the drop tower. And then finally, well, as mentioned earlier, one of the functional requirements is to allow rotation about the X and Z axis. Shown on the right, the helmet position has a range from 90 to 45 degrees with the resolution of 11.25 degrees, as well as allowing the helmet to rotate. And then another component of the frame and arm subsystem is the arm stopper. So the arm stopper has 2 purposes. It's designed to set the initial position of the arm prior to impact, as shown in figure A, as well as preventing the arm from swinging back into the drop tower after impact. This is shown in figure C. So once the helmet is struck, the pendulum arm will swing back, and the swinging arm or the swinging member of the stopper will lock into place of the gear rack. I forgot to mention, but the arm stopper is composed of 2 weld-on tabs that will be welded onto the bottom of the pendulum arm, a swinger arm that will have to be manufactured, and a gear rack that can be bought off the shelf. So this whole system, the gear rack will be attached to the cross members of the structural frame. This will also be done using bolts and L brackets. So now I'm going to pass it off to Randeep to further discuss some components of the frame and arm subsystem.
So a wooden prototype was built of the pendulum arm shown in figure A and the head and neck adapter shown in figures B and C to study their behavior during an impact test. These were built around a pre-existing beam and shuttle with a few modifications made to the shuttle. This was originally designed with the idea that we would use aluminum T-slotted profiles made by 8020 as our final design. Because of this, we wanted the top brace member, indicated with the red arrow, to be adjustable using the 8020 aluminum solutions. Due to the impact test on the prototype, we observed that the top brace member actually sheared off after continuous impacts, and the shuttle had excessive vibration due to the impact force. Both of these observations were taken into account when creating the final design. So our pendulum arm is constructed of a 6 by 3 inch profile cross section made of aluminum rectangular tubing with a 1/4 inch wall thickness. And as you can see from figures A and B, it is now rigid due to all the components being welded together to offer a more permanent connection and to avoid any potential shearing of the top brace member as it did with the prototype. This also offers a more cost-effective approach as opposed to using 80-20 aluminum profiles. The purpose, of course, it serves is to hold the head and neck assembly and rotate about a pivot after the impact event. In addition to that, the brace members act to distribute the impact load. The pivot, otherwise known as our connection, the method in which this arm is allowed to rotate is by a 2-inch diameter steel round bar that goes through 2 mounted ball bearings as shown in figure A. And just outside the ball bearings are hinged collars to prevent it from sliding along the axis of the steel round bar. We also included low carbon steel spacers inside the tubing to prevent any unnecessary compression of the tubing and to also allow for the bolts to be fastened. On the bottom portion of the arm, we've included a region where we can add standard Olympic weights to study the behavior of added mass to the pendulum arm. Next, I'm going to hand it over to Vu, who will talk about drop shuttle and guiding rails.
All right, so thank you, Randy. So a drop shuttle is a critical component of the drop shuttle since it serves as the impactor for head and neck pendulum, and then it carries the testing object on the head drop side. A drop shuttle contains a subplate, which is attached to 4 ball bearings guided on 2 monorails. The drop shuttle carries a 45 degrees angle steel anvil to collide with a testing object. In this case, is an instrumented hybrid 3 head and neck covered with the testing helmet. And the shuttle collide at required impact velocity, which is 8.5 meters per second. The anvil is a 6 by 6 inch square with a thickness of 3/4 inches to ensure the toughness and surface contact during the test. A flag is attached to the shuttle so that the velocity gate will record the impact speed. So to effectively study the rotational energy caused from the drop test, the shuttle's weight would need to be as heavy as possible to cause significant effects on the testing object. So additional components such as steel plate could be added to the shuttle as shown in the figure to the right. Before the test, the shuttle will be lifted up and by using quick release and lifting mechanism, which will be discussed later on in the presentation. Additional ball bearings is used to keep the quick release from hitting the linear shafts while traveling up or down. In the next slide, I will talk about the guiding rails. So the guiding rails are used to guide a shuttle when it is lifted or dropped vertically from gravitational force. In the design, 2 monorails are bolted to a subplate, which this plate will be then welded into the steel I-beam. The beam is 20 feet tall to ensure the traveling distance of the shuttle to reach 8.5 meters per second impact velocity. Ball bearings are used to create a frictionless motion. The rails are hardened steel shaft with 1/2 inch diameter, which are commonly used for drop test application. That will conclude my part for now, so that Pablo will then take over and then talk about the drop ring and stopping mechanism.
Okay, thank you, Vu. Okay, so this is a drop ring that's associated with the linear impact side of the drop tower. The shuttle design itself is very similar to the one Vu already explained with the rails and the 4 bearings. The function for the drop ring is to guide the helmet, which will be placed on top of the drop ring, to the anvil located at the bottom of the apparatus. The ring itself measures 24 inches and 10 inches wide to ensure there's enough spacing for the helmet to be placed in any position and orientation. The long parallel arms are used to translate the helmet along the parallel arms for various impact points, not through the center of gravity. To hold the helmet in place, we have designed aluminum pins with the rubber balls used for grip. And then the pins will be adjusted by releasing the thumb screw that is located at the side of the drop ring and then locking it back up when the position has been adjusted. The design, the lower, I also mentioned have the attachments on the drop ring, and the attachments were to prevent some of the moment that is going to be affecting the ring by the helmet weight and then the impact after it hits the dampers. Sorry about that. Yeah, thank you very much. Here are some examples of the various orientations and the locations that you could put the helmet. In the pictures A and B, you can see that we can orient the helmets in various orientations and they would still hit through the center of gravity. Or then if we see figure C, I'm sorry, we can translate the helmet pins and the helmet towards the edge of the ring to make more oblique impacts. Next, I will talk about the stopping mechanism. For the stopping mechanism, we decided to go for hydraulic dampers. The reason why we went with hydraulic dampers is because they have a high energy absorption. So what I ended up doing was I ended up calculating how much the shuttles how much energy would be produced by the shuttles, and then chose a specific damper for that purpose. I'm sorry, the purpose for those purposes. As shown on the, I put the damper properties on the side, but the ones that we want to focus on the most was the max energy per cycle, which is 6,800 Newton meters. And when I calculated, the shuttles were 3,000 Newton meters. So it proves to be very effective. And also the other thing that I wanted to focus on was the deflection. After calculations, if I assume 100-pound shuttle, then the dampers would deflect only 3 inches out of the 6 that are mentioned in the stroke length. So so the dampers proved to be effective for both shuttles. In the next slides, we will be explaining the sturdy anvil.
All right, thank you, Pablo. So on the free head drop testing method, a sturdy anvil is acting as a test bed. So a sturdy anvil components include a 6x6 inch base plate, a 5-inch diameter cylindrical post, and a 5-inch diameter replaceable impact anvils. So steel is chosen as a materials for its strength and hardness. So detachable anvil comes in different geometries such as flat, 30, and 45 degrees angle to allow operators to study different effects of rotational energy caused onto the testing object. The method of manufacturing will include both welding and bolting. So in the next slide, I will talk about the stress analysis of the sturdy anvil. So we performed the nonlinear dynamic simulation to see if the design will be safe to build in practice. So in the simulation, the testing object was assigned to be collided with a sturdy anvil at 8.5 meters per second. So the high stress concentration appeared to be at the connection between the cylindrical post and the base plate. However, the stress is still below U point of steel, which is 3.5 E to the power of 8 Pascal for 20 cold rolled steel. So the design is safe. So in the next slide, I will pass over to Heriberto to talk about the lifting and releasing mechanism.
Thank you, Vu. So now I'm going to discuss the shuttle operations. So these are the retracting and releasing mechanisms used for the shuttle and the drop ring. Since one of the major project requirements for us was to have repeatability in our trials, we had to incorporate a method that would allow us to run multiple tests with the least amount of idle time and setup time. So here you can see a retracting mechanism that the team incorporated into the design. This is an electric hoist. The electric hoist is designed for lifting loads that would be impossible for people to lift. The electric hoist is reliable in strength, safety, and speed. In the design, the electrical hoist will be used to lift the shuttle and the drop ring, which independently both have 4 bearings attached to the guiding rail, and they both run in the vertical plane. The electric hoist is attached to a subplate that is then attached to an I-beam that runs perpendicular to the vertical mainframe. The hoist that we chose was 40 pounds in weight, 120 volts, 60 hertz efficiency, can lift up to 1,500 pounds, as high as 30 feet, and at speeds of 33 feet per minute. So this hoist has a 360 Z-axis swivel hook that can remove a load at any angle, and it has a 3-button control system that with a 40-foot, 0.20-inch diameter cable that prevents it from getting in between or cuts off, so the operator can access it. So by pressing the button, the shuttle retracts or the drop ring, respectively, and the hoist will vertically pull the system upwards as it's attached to another C-catch quick release system, along with a lifting eye-bolt that's attached to the shuttle that will be used to release the shuttle and the drop ring when tested. So in the next slide, we can see our release mechanism. This is our C-catch by Macmillan design toggle release. It's a standard model that uses a hitch pin lock for locking safety that prevents the dropping of the load. So the quick release mechanism releases the shuttle as it retracts by the electric hoist and allows the shuttle or the drop ring to reach 8.5 meters per second therefore meeting another one of our major project requirements. So the release mechanism offers a combination of high strength and hardness, plus it's very transverse in mechanical properties. The quick release is attached, like I mentioned, to the electric hoist on one end, and on the other end uses the quick release the steel lifting eye bolt that's attached to the shuttle. So the eye bolt has a vertical capacity to lift of 5,000 pounds. It has a 2-inch shank length, and it's 1.5 inch in eye diameter. So this release mechanism is activated by removing the hitch pin, pulling firmly on the release lanyard that's connected to the end release of the lever. It can be activated in any direction within 90 degrees perpendicular or parallel to the line of load. So it's safely, the safety lock allows it to be released without actually requiring a load on the system. And the quick release will also run along the guiding rail that prevents any impact to the system after we release the shuttle or the drop ring, which will cause any unnecessary vibration or damage on the mainframe. Because the point of this is not to have any parts that just dangle around for safety measures. So in conclusion, our team was able to model and perform a detailed final design of the 60 helmet drop test apparatus using SolidWorks. We were able to model and study the pendulum arm using a prototype design based on wood and assembled using an existing I-beam and shuttle system. So based on the shearing cost on the top member and the excessive vibrations after the continuous impacts during the testing, the frame and armature team was able to redesign accordingly. So these prototype trials are reflected on the modifications towards our final design. Unfortunately, due to the inability to build and physically test the final SolidWorks model, along with the manufacturing stage that was halted, our final design can only be validated through simulation testing. So, however, more testing can be performed to validate the final design, and more improvements can be made in the future. So now our team would like to acknowledge Dr. Raymond, Mr. Sergio Marquez, Mr. Robert Resinger, and Makerspace for their help in research, design, and testing of the project. Your guidance really facilitated the project for our team, and we're pretty grateful to have learned so much under your expertise. So thank you on behalf of the team, and well, this concludes our presentation. So any questions?
Robert, do you have a question?
Hey, Dave.
Hi.
No, actually, I just was turning my mic on there. Just wanted to say thanks to all the guys for all the hard work. It was impressive to watch the project progress over the time period and see how much they evolved from what started out originally to where we ended up. Good job, guys.
Thanks very much.
Thank you, Robert.
Thank you, Robert.
So I have a question for the team. Can you guys go maybe to like the first slide showing the frame assembly?
Yeah. Just give me 1 second.
All right. So I really like a lot of the CAD work you guys did. You obviously did a ton of planning. I was a little bit curious how you came up with this frame design, and was there any requirements for compliance in the system? And you know, is there, like, I noticed there's a couple spots where, you know, is there, like, you might have, so you see when if you go back from the helmet and then it goes right up, you don't tie it into the node of kind of this, your big swinging piece of material. Like, you don't tie it necessarily into like the node. So there's a couple places where you put tubes and bending and that sort of thing. Do you guys, and then also maybe I'd also think about the torsional rigidity of it. Do you guys have any like metrics associated with how much compliance you can have in this frame, or do any FEA to see about kind of the stresses anywhere inside of this thing?
The only thing we did do was it was just a static FEA analysis. We didn't get into the dynamics of it.
Static's fine.
Okay, yeah, I mean, it was just basically the weight of the arm and all the components it has with it.
Oh, gotcha. You didn't look at the forces from impact though.
No.
Okay. And then I guess I had one other question was, so the quick release mechanism is way up there at the top, right?
It's being pulled by
It's like a long lanyard or something. You can, I heard you say lanyard, but I was wondering how do you release that baby?
So it's like a hitch and pin. So just imagine like a lever. So you just pull the lever and
But it's 20 feet up in the air, right?
That's why it's a pretty long lanyard. It's a 40-foot lanyard.
Okay, gotcha. I was like, you got a big string that goes up to it. Okay, very cool, very cool. Yeah, I like a lot of the work you guys did.
I'll just add that the team, this design you see in front of you here is fairly recent. The team went through a lot of iterations of how to support the arm and the arm design itself. Originally, the support structure actually was going to be attached directly to the vertical mount, the vertical tower itself.
Gotcha.
And so we spent a lot of time analyzing that, and so you know, there was quite a bit of analysis done on previous designs, but yeah, we didn't quite have enough time at the end to do dynamic analysis on this structure. I do have a question. I guess question comment, if I might. Slide 12. Can you guys turn to slide 12? Yeah. Alejandro, this is a good graphic, by the way. This is this cool design Alejandro came up with. That a really good thing about it is positioning wise, where the head doesn't change its position dramatically, so it makes setup for different test angles, I think, easier. One thing that I think we might have to continue to do if this design goes forward is if you look all the way over to the right at the 45-degree angles and maybe even the 56.25, I think we're going to have a situation where we're going to potentially crash into the horizontal beam, because the drop member is going to come down vertically and the head form is going to deflect downwards, flex, and especially the top one there, you see there's only about maybe an inch or so clearance of the chin bar to the horizontal beam.
Correct. Yeah. So I was thinking perhaps making the attachment either longer or I guess higher from the arm.
Yeah.
I think, Dave, the topic was in our last meeting that we touched on the notion of having an adjustable set point instead of having a static set point, and to try to adjust the helmet by sliding it back and forth on the rail would alleviate the cantilevered section of that beam underneath the helmet.
I see.
And keep the helmet mounted out at the end, and then just have an adjustable set point.
Yeah, right.
I have one question about this slide. I think this is a lot of work, I think. You guys did a lot of good work. Yeah, impressive. This frame armature, this structure can also endure kind of a torsional impact. Torsional impact is also, did you guys consider kind of a torsion?
No, we didn't look into that.
Okay.
Guys, do you have the measurement of the footprint of the entire system?
I have that somewhere. All right, so
looking that up, if Hasmik wanted to get a photograph or a screenshot of our pictures, so that if some of you don't have your cameras turned on, if you don't mind turning them on for a second, that would be nice.
So it's about, the footprint would be about 9 by 3 feet. That's including the base plate that holds the sturdy anvil, tower, and the footprint of the frame itself.
So I guess I have a question too. So in terms of the project, what are kind of what does the group see as kind of your next steps? Let's say there's going to be another team of students taking this on. Where do they go from here? They basically just hit the ground running building? Is there a little more analysis and design to do? What would be your advice for the next team?
In terms of the arm and the head and neck attachment, I would say, I guess more analysis needs to be done to really understand how the neck is going to react under impact, as well as how the arm is going to react. Our prototype showed us a little bit of how the arm would react after impact in terms of how much it swings back. But something we took into consideration was that it was made out of wood, and it was being struck by an aluminum shuttle. So I'd say a little bit more prototyping would have to be done to really understand how the arm would react. And then something we weren't able to get to because our prototype broke a week before the labs closed is actually adding mass to the arm to see how much the swing is affected and how much the neck is affected with an additional mass added.
So yeah, to follow up on that, I would say some dynamic simulations would have to be performed before the next team starts to start actually constructing the entire tower.
And I would like to add on to that as well in terms of the shuttle itself. Since the shuttle are running on to 2 monorails, which are just used based on the ball bearings. Because of the mass of the shuttle is pretty large, so they would have to consider the moment caused like after the impact, because this obviously is oblique impact. It doesn't collide right below the center of gravity. So it will cause a moment. It might be large enough to pull the bearings out of the system. So something like to counteract the moment, something like maybe like additional rollers to be attached to the backside of the I-beam so that it can prevent that, like, from being breaking off. That are something like, I would advise if the next team is taking over and then start doing more analysis on it.
Very cool.
I have a question for the senior design team.
Yes.
First of all, kudos to the students. My name is Humberto Egos and I work at East LA College. I'm currently the chairperson for the department. I'm just stoked because I noticed a couple of our students from our department are presenting in this project, and I see a couple of the students in the gallery. They're also participating as guests, so I'm just stoked that I get to see them again. But so first of all, great job on the presentation, and we have had Dr. Raymond at our school as one of my guests, and I have always been fascinated with the type of research work that he's been doing with his students. So I'm just glad I was able to walk into this virtual room and get to see it again through the senior design students presentation. So I'm glad I made it. And so I have a couple of questions. So I know you guys are, I guess, don't have access to being able to build this physical model, but how much of a big difference would it make if you do build it and then you have your simulation results? How much of a difference would you have expected to see in the physical model compared to your numerical model? Because maybe that's all you need. So I'm just curious to see how much of a % difference would you have seen between what actually takes place through a physical model and through your results through this simulation. And then number 2, I'm just curious to see how you guys were able to, I guess, get together and improvise on your senior design, given that you guys were not expecting to go virtual on this project. And so how much of that dilemma had an effect on your deliverables? I didn't catch the first few slides, but were you guys expecting to deliver a full scale physical model and then rely on the physical model, or did you guys have to improvise and go with the numerical results? So those are my 2 questions for the group, and I'll go ahead and mute myself now because my kids are making a lot of noise here.
Yeah, so in terms of the first questions, you're asking like the percentage difference between the numerical results comparing to like a practical model. To be honest, I cannot for sure tell you that. Well, I mean, like, the practical model will be the practical model will be a lot different comparing to the numerical results that we got, because I mean, like complicated nonlinear dynamic simulation must have to be performed in order to produce like because like we put the safety on top of everything else, so that if we cannot say for sure that that one's going to be safe to build, more tests have to be performed in order to actually buy materials and then start building it up. And then the scale of the project is really large. Like the beam has to be like around 20 feet tall. And then in terms of the capability of the facility that we have in the lab, it's kind of like hard to actually build it up and then transport it.
How about the change in plans because of the health situation we're going through? How much of that had an effect on your delivery, on your deliverables?
Pretty
Significant. Yeah, Randy, can you, yeah.
Like Alejandro had mentioned earlier, we were unable to do further testing on the prototype, which was built in Dr. Raymond's lab. So we would have liked to, have more trials with the head and neck adapter that was built, and also study, possibly even reconfigure the arm because like the top brace member sheared off. So potentially we may have had more time to, add a new brace member on there and continue testing, to further, adjust our final design.
Okay. Well, thank you, team, and thank you, Robert, for participating with us this year. We need to bring this presentation to a close. In just a couple of minutes, the RoboSub team will be preparing or will be presenting their presentation. Congratulations to all of you on the 60 helmet team. It's a great job.
Thank you
very much.
Thank you much, guys.
Thank you.
Thank you, guys.
Thanks again, guys.
All right, thank you, Robert.
Thank you, Robert, Raymond. Thank you.
My pleasure.
Well, not too far. We've got the RoboSub presentation coming up right now. Who from the RoboSub team is going to drive the screen?
I will.
Okay. Let's see. Are you able to take control of the screen?
Yeah, looks like it.
Okay.
Can everyone see this? Can everyone see my screen?
Yeah.
All right. Okay, let me just make sure. That everyone is here. Is everyone here?
We've got a couple of minutes.
Okay. Yeah, I'm just gonna go through all the people that are here and make sure our whole team is here.
We've got about 40 people in the room right now.
Stephanie, are you here?
Yes, I am. This is Stephanie Pell.
Sorry, looking for Stephanie Godina. Sorry about that.
Okay.
Stephanie Pell, if you want to step up and join the RoboSub team, we could make arrangements.
Please.
I was wondering why he was calling me out.
No, I don't see Stephanie on the list right now.
Professor Thorburn, I've sent you a message on the chat if you could read it.
Okay.
Thank you.
Looks like Stephanie is connecting right now. Stephanie, you're here now, right?
Yeah.
Cool. Okay, so Arnold, Danny, Stephanie, Sidra, Kevin. Kevin's here. Okay, we are all here, so let me get this started. So I think Sidra will be starting off the presentation whenever she's ready.
I don't know if you got the same thing, Mike, but the bar, I think, Joseph, for your video, can you move that off or like minimize it? It makes it black, makes part of your screen, part of your slides black.
Oh, gotcha. Okay.
Yeah, that's much better. Yeah, perfect. All right,
Yeah.
I think you're good.
Okay.
Okay, should I start?
Yeah, if you're ready.
Cool. All right, thank you all for coming. Hi everyone, we're team number 50, the International RoboSub competition team. My name is Sidra and my teammates who will be presenting with me today are Joseph, Kevin, Stephanie, Danny, and Arnold. Our faculty advisors are Dr. Hei Shen, Dr. Mark Tefunction, and Professor Richard Cross. Next slide. First, we'll be providing you with some background about the project, followed by a discussion of the mechanical and electrical systems and subsystems, and finally some concluding remarks. Next slide. Autonomous underwater vehicles are self-controlled submarines that have environment sensing capabilities to allow them to perform tasks without human intervention. AUVs are used in several applications, including military operations, biological research, pipe cleaning, and many more. Next slide. Pictured here is the vehicle developed in 2018 by the CSULA RoboSub team. Every year, the team develops a new AUV for the competition. Next slide. The RoboSub competition is an annual competition taking place at the Navy Transtech facility in San Diego. Each year, over 50 teams from countries all around the world bring their AUVs to the RoboSub competition to compete in various tasks underwater and score points. Next slide. Examples of some of these tasks are displayed here. On the left is a task requiring the AUV to pull down a lever and shoot torpedoes into a slot with the correct colored border. In the middle are buoys shaped like dice, where the points for that task are dependent on the numbers the submarine bumps into. On the right is a large roulette wheel, where the sub would drop golf balls into the different slots to score varying numbers of points. The teams that accumulate the most points in semifinals get to compete in the finals, where the team with the most points at the end wins the competition. Next slide.
Hi everyone, my name is Joseph. I'm the mechanical systems lead. So our organization is composed of 2 senior design teams with their own faculty advisors, and our engineering senior design team is broken down into the major subdisciplines of mechanical engineering and electrical engineering. And each of those sub-teams have 3 people assigned to specific tasks. The requirements for our vehicle are primarily driven by the RoboSub competition rules, which place constraints on things like weight, overall dimensions, the buoyancy, and the type of power source we have. Our budget was divided as shown, with most of it going to sensors and the rest being allocated to raw materials for the mechanical systems, as well as manufacturing costs. So at the highest level, our project's schedule in its simplest form was a design, build, test schedule, in which we designed in the fall, started manufacturing over winter and in the beginning of spring. And before transitioning to online, we were on target to start testing in the middle of March. And that would continue up until the competition in August. So now let me present overall mechanical systems concept. So our overall mechanical system is shown here on the left, and it's made of 3 primary subsystems, those being the hull, the frame, and the actuated systems shown on the right. So now let me dive deeper on my specific portion of the project, which was the hull. So the hull design this year, we went with a box shape to conform to the electronics that it encloses. And it's composed of these welded sheets of aluminum that will eventually be anodized, and a removable lid made of acrylic that gets latched down to compress a flat gasket seal to protect the electronics from the environment. So one of the main functions of the hull is to provide the interconnection between the sealed electronics on the inside to the electronics and sensors on the outside. So we have things like PCBs routing to things like sonar, DVL, and hydrophones to this rear connector plate that's removable and O-ring sealed. The connectors that we use are subsea connectors made by Seacon. Now, one of our key design features for the hull this year is a design for serviceability. And we've accomplished this by making an electronic shelving system that is entirely removable and can be folded out for any servicing or testing that needs to be done. In order to verify the strength of the latch points, which was sort of an area of concern after manufacturing them, we did a static analysis in SOLIDWORKS to determine the required weld size to achieve a factor of safety of 3. In order to further verify these results, I took a quarter model and meshed it further in ANSYS, and then also performed a fatigue study to determine that the life of the assembly under the expected loading conditions could meet a factor of safety of 3 for infinite cycles. And now I'm just wanted to show a slide of kind of where we were at with the pictures that I had on me, and sort of the myriad of manufacturing processes that were used, and all the manufacturing was conducted entirely at Cal State LA. And before transitioning to online, we were just about ready to start welding after we finished milling the connector plate. Let's now pass it off to Kevin to discuss the frame.
Thank you, Joseph. So hello, my name is Kevin, and I'll be going over the frame design concept. Next slide. So this is the frame design that the hull will rest on top of, then latch together. This new unique design was created with modularity and ease of access to components in mind, compared to previous generations of subs. So the purpose of this frame is to provide mounting surfaces and avoid direct mounting to the hull that would add points of failures that can compromise its water sealing. The choice of materials were chosen to have good corrosion resistance because the operating environment has some salinity to it. And the frame primarily uses aluminum because of its good specific strength and is easy to be seen, with the screws made out of stainless steel. Next slide. Here's the bottom of the frame showing the general placement of some of the components from the list on the left. The components are mounted onto the rails using a design similar to a skeletonized version of T-slot fixture plates. So if a component needs to be replaced or moved, then it can easily be slid out of the rails with the undoing of a set screw. Heavier components such as the ballast weights for the buoyancy control are mounted onto the side as shown. Next slide. So this is a close-up example of how the components can be easily inserted or removed from the AUV. So on the left picture, you can see the sonar sensor being mounted on 2 rails that slide into the T-slot fixtures. You can also see the mechanical claw and torpedoes already mounted to the frame. And so we use cone-shaped set screws that will be used to prevent the part from moving as shown in the right figure for securing the hydrophone sensor in place. Next slide. So we did some optimization. The supporting legs of the frame started out as a large block of material, which then a basic profile was cut out, shown on the left picture. Then a topography study was created for the best strength to weight ratio, with a goal of removing 3/4 of the materials shown on the middle picture. And finally, the design shown on the right picture is the cleanup version with some slight tweaking done to it. Then it is also important to retest the part to see if this design is still valid. And next slide. So this is a comparison of the original part to design A and B shown in the table. So design A is another method of topology optimization by following the principal stress lines, then slightly adjusting the orientation to get the best possible safety factor. Design B was from the previously shown slide. So I went with design A because it is a stronger part of a higher safety factor, and it's only slightly heavier than design B. Next slide. So I will hand our actual systems to Stephanie.
Hi, my name is Stephanie Godina, and I oversaw the actuated systems for the AUV. Next slide. First off, the reason for having actuated systems on the RoboSub is to gain points during the competition by completing different tasks underwater. The actuated systems break into 3 different mechanisms to perform 3 tasks. The 3 tasks are shooting a torpedo through a target, releasing a marker in a designated location, and grabbing an object. In the following slides, I will go over the designs for each actuated system. Next slide. The torpedo mechanism is an all-pneumatic system that allows it to deliver the required pressure into the torpedo. This design was inspired by previous teams who have successfully performed the task underwater. The torpedo itself has been modified to have a better flow regime. It also consists of the following items and has the estimated parameters as shown. The way it works is as follows. The bucket changer is mounted onto the ASA regulator, which is connected to a 90-degree fitting and connected to a variable pressure regulator to decrease the CO2 pressure from the cartridge to the desired value. Then it will be mounted into the 2-way solenoid valve, where in one of the pipes, the torpedo will be held in place by an O-ring. After the whole system is pressurized with carbon dioxide, a signal will be sent to open the valve, allowing the CO2 to escape the pipe and propel the torpedo forward. A turbulent viscosity simulation was attempted on the torpedo. The simulation itself was used to determine how the surrounding flow would act against the torpedo when launched at a given velocity. Repeating the simulation at different velocities outputs a standard flow regime that can be shown on the above simulation. The flow regime shows that when the torpedo is launched, the flow around the entire torpedo remains in a laminar state with no disturbances around it. Next slide. The dropper mechanism uses one DC motor that will operate at a slow pace to release the markers into the designated area. The dropper consists of the following items and has the estimated parameters as shown. The DC motor that is used in the system is the same motor used for the thrusters in the RoboSub. The motor has been used in previous years, so we know that the motor will have no problem operating underwater. The motor is connected to a rotating platform, which contains the markers, and after rotating, they will be released underwater. The system can hold up to 3 golf balls in order to have multiple attempts to place the marker in the designated area. The dropper also includes a lid to be able to refill the system with easier access. Next slide. The gripper is responsible for being able to grab and release an object underwater. The design itself operates on one servo motor that rotates the gears to grab and release an object. The fixed arm allows the gripper to remain at a given location. When the underwater servo motors were purchased, we concluded through testing and research that it could not be determined if it will operate functionally in the conditions that the RoboSub will go through. One of them is the depth that the sub will go in and the servo motor not being able to function at that water pressure. For the gripper, many challenges arose with the actuated system, but the main challenge was being able to get the servo motors to operate underwater. Other solutions that were beginning to be looked at was creating a successful servo motor enclosure and creating an entirely new claw mechanism made using a pneumatic system. Now I will pass it on to the electrical team.
Okay, now I'm going to talk to you about the overview of our electrical system on the autonomous underwater vehicle. Next slide. The electrical system consists of a motherboard, microcontrollers, and a sensor suite. The IMU produces angular data and the barometer produces pressure data. These sensors are used for various navigation tasks. Since previous CSULA RoboSub teams have already developed sufficient programs for the use of these sensors, the 2020 team did not develop new algorithms for them, but instead used the algorithms already developed. The RoboSub computer science team worked with the DVL, cameras, and the motherboard itself to provide the sub with positional data, object detection capabilities, and autonomous decision-making. We won't be talking to you about those because there's a separate senior design team that worked on those components. And that leaves the hydrophones, power distribution, and active sonar systems for this year's electrical team to develop, which are the 3 components you'll be hearing about shortly. Next slide. So first, I'm going to talk to you about the hydrophone system. Next slide. In the competition, some objects have sound emitters called pingers located on the floor near them. If the submarine can determine where the sound is coming from, it can navigate to the object to attempt that task. In order to do this, the submarine uses special microphones called hydrophones, which are meant for detecting sounds underwater. This navigation based on sound is called acoustic localization. Actually, your brain uses acoustic localization to determine which direction sounds around you are coming from. It's based on which ear receives the sound first. This can be electronically replicated by 2 or more hydrophones if we can determine the time difference between the sound signals received by the hydrophones. Consider the pinger and 2 hydrophones shown in the diagram. The sound travels from the pinger to hydrophone B first. Next slide. And hydrophone B receives the signal first. We call this first time T1. The graph shown is a short sample of the signal received by hydrophone B. The signal continues traveling in the plane until it reaches hydrophone A. Next slide. Which receives the signal at time T2. Notice that the graphs are the same sound wave, but shifted over. This is easy to see when the graphs are, when the signals are plotted on the same graph. Next slide. Tau is the difference between the arrival times of the signal at each hydrophone. Now you might be wondering why this is useful for determining the location of the pinger. Next slide. Tau can be used in this formula for the heading angle, where V is the velocity of sound in water and L is the distance between the hydrophones. To understand what information this heading angle gives us, take a look at the diagram. The submarine is facing away from the pinger by some angle theta, which is the aforementioned heading angle. And this angle tells the sub what angle to turn in order to face the pinger. Our goal in navigating to the pinger is to minimize the heading angle. Next slide. Providing us with a straight path to the pinger. So we can calculate the heading angle easily using the time difference. Determining the time difference then becomes the key task in developing a sound localization algorithm. The most commonly used method to determine this time shift and the method that I employ in the code that I wrote is cross-correlation. Next slide. Cross-correlation works by shifting one signal over the other and computing the correlation at each time shift. The time shift with the largest correlation is the arrival time delay between the 2 hydrophone signals. The cross-correlation method has been developed and tested with an array of 3 hydrophones in air, with 2 of the hydrophones used for determining the heading angle and the 3rd hydrophone used to determine whether the sub is facing the pinger or 180 degrees away from it. While the system's accuracy must still be quantified, a qualitative observation concludes that its functionality is sufficient for navigating the sub to the pinger. Next slide. Now, the hardware implementation of this system is displayed in the block diagram shown here. After developing an algorithm for determining the time delay between the signals using cross-correlation and then calculating the angle using this time delay, this can then be implemented in the overall system to allow the sub to use data to navigate to the pinger. As displayed in the diagram, the sound waves in the water are received by the hydrophones, then these signals get amplified, and after that, sampled by a data acquisition system. This produces a signal that can be analyzed by the motherboard. The motherboard then does the necessary calculations using cross-correlation to calculate the time difference and then the heading angle. This gets sent to the microcontroller as the desired angle, and the IMU provides the microcontroller with the sub's current angle. Once this information is known, the microcontroller produces the appropriate motor signals for the submarine to move to the desired angle. Next slide. And now I will pass it off to Danny to talk about our power distribution system.
Hi, my name is Danny, and I will be talking about the power board. Next slide. So the purpose of the power board is to help transfer and manage electricity from the power source. The source of our power is going to be a single 14.8 volt battery. The board is going to support the devices and microcontrollers that are going to be used for the vehicles. The board will also allow each component to perform at a certain power. As shown here in the block diagram is an overview of what the power board is going to consist of and how it's going to be constructed. Next slide. Here is a breakdown of the requirements needed to operate each of the devices and microcontrollers that are going to operate the vehicle. The voltage output produced from the board will help distribute the correct power to prevent any damage that could be done to the components. The PCB will also manage the power consumption to avoid excessive heat production and current draw. Many of these components have been used in the past competitions, so powering them will not be an issue. Next slide. To operate our components, a buck converter is needed to drop the voltage. The converter used for the AUV is a LT3976 IC chip. This helps bring down the voltage and gives us more space on the PCB. The chip is ideal for low current with a max output current of 5 amplitudes, which is ideal since every component besides the motherboard will be operating at no more than 4 amps. The chip also operates between the input voltage range of 4.3 volts to 40 volts. The image on the bottom left is the circuit design of the chip used to produce the ideal values that we want shown on the right side. The top right is the results of the required output voltage that we need, and the bottom left is the result of the output current for the 5 volt output voltage. Next slide. Even with a converter that works, we still need to ensure that the board will perform consistently. Therefore, the LTC4353 IC chip was also included to the design. The chip helped minimize the reverse current transients current transfer, allowing it to save power and board area, meaning that we also do not need to use a heatsink. This way the chip works is through its external end channel MOSFET. When the input voltage goes below its output threshold as shown in the graph below, the MOSFET will shut off and match the performance of diode, which lets the device perform effectively. Next slide. The design of the PCB, as you all can see here, is the full design of the board. This was created for versatility and optimal usage. The method of mounting the components is the surface mount method, aside from the headers, which is a through-hole method. This board contains 18 headers, plus an additional header for the 5-volt, 7-volt, and 12-volt, for a total of 21 headers. The extra headers are included in case we decide to use more components later on before the competition. With the amount of space saved, the dimensions of the board are 4.3 inches by 3.5 inches, which gives us more space within the vehicle itself. Next slide. I will now hand it over to Arnold so he can talk about the sonar.
So hi, I'm Arnold. I worked on the sonar, and I'll tell you a little bit about it. Next slide. So the sonar system has two primary components, a sonar module and a microcontroller. So I'll tell you first a little bit about the module. So the module is a self-contained unit with transducers that both emit and receive filters and a logical circuit that processes a lot of the acoustic data that's being produced. It then communicates that data to the microcontroller, which does additional processing to report ultimately to our main computer system. Next slide. So here I have a sample of the kind of data that the module produces. So as you can see, there's quite a bit of distortion. And the color coding here indicates red is high intensity, yellow is moderate intensity, and blue is low intensity. So as you may be familiar with sonar, it works off of reflection of sound waves in water. So based on the intensity of the reflections, that information is then processed into range and confidence and into an intensity array known as a profile, which is then sent to the microcontroller and processed further. And to give you a better sense, the next slide. This diagram effectively shows how the data is processed. So here I have a common situation where the module emits sound toward an object and a wall. At the bottom, I have the corresponding intensity values that would go along with the objects it encounters. So when there is no object, intensity value is low. It peaks when it comes across an object and then peaks again if it comes across a limit. So this data is then compiled by the module into an array that's sent to our microcontroller and processed to determine whether there's an object, how far away the object is, and whether there's a wall on the opposing end. So it effectively acts as a detector and a proximeter for both walls and objects. Next slide. So far, we've been able to detect objects at up to 7 meters with approximately 10% error. Walls, because they reflect almost the entirety of the sound wave, have a greater range at 30 meters and a greater precision as well at within 5% of the reported proximity. As of now, currently we're working on the algorithm to reduce instances of false alarm and to have a dynamic sensitivity for when there is no object detection to increase it so it can actively adjust and more frequently detect objects. And now I'll pass it off to Joseph, our mechanical lead, for closing remarks.
Okay, so that concludes the RoboSub team's presentation, and we just like to take the last few moments to thank our sponsors, our advisors, Dr. Function and Dr. Shen, as well as all of you for being here. Thank you. And now we can open it up to any questions you may have.
Hello. Hi. This is good work. It seems to me this is excellent work. I think one of you mentioned about power consumption. do you have a requirement about the power consumption, and do you have any kind of a measurement or check up against the power consumption requirement? Do you have that kind of a presentation?
Is anybody going to answer?
Danny, do you want to take that? Or Sidra? Hey, Danny, your mic is muted.
Oh, sorry. Can you repeat the question?
Okay, I heard that one of you mentioned about power consumption around slide number, I don't remember exactly, around 43 or 45, 44. Power consumption, do you have any kind of requirement about that? Or do you have some analysis about your power consumption of your algorithm?
So the power consumption, we don't have too much of an actual requirement. Our goal is to simply just make sure that it doesn't produce too much heat to the point where it ends up damaging the vehicle itself. So we're going to end up having some of them connected to the railing within the vehicle itself, so it can absorb some of the heat.
Okay. Another question I have is one of you mentioned about fatigue analysis of some structure. Do you have a presentation about the kind of a safety factor or margin of safety about the fatigue analysis?
Yeah, we used a factor of safety of 3.
Okay. That's it for me.
Dr. Gallagher, or from?
My name is Austin Park.
No, I understand. Yes, Dr. Park, I know that. I meant somebody else had raised their hand earlier. Okay.
I have a.
Can you turn to your last chart, please, for a second?
Yeah, you want me to give a slide number in mind, or this
The very last one?
This one, right? Or?
Maybe it was the one where you had estimates of the uncertainty in your distances, or in your there.
Sorry, let me move
Although you've got something blocking your screen.
Yeah, sorry. Here, right?
Yeah, right. So you say that for object detection, you say 7-meter range with 10% position error. Is there did I miss how big an object that is? And when you say 10% error, is that like angular error or range?
It's a range error.
A range error?
Yeah, and so the thing with sonar is that it's kind of proportional to the distance.
Right.
So at very close ranges, I want to say within, I tested with certainty within 2 meters, but I suspect 3 meters would yield about the same results. We were actually detecting really small objects. I was detecting an apple. So we're talking about like a 2-inch sphere, a 2-inch diameter sphere is detectable, which is pretty, it's kind of the kind of result that I was looking for because it's not, because it's of its its curvature, it's not as reflective as, let's say, like a flat surface. So and at 7 meters, I was able to detect a bucket. So we're talking about objects that are more like in a foot diameter. So it ranged, yeah. So that our maximum was 7 meters, and approximately objects that are about like a foot wide. We're talking about like a square foot of area.
Okay, because you said a wall at 30 meters, but the other one you didn't give any indication as to how large the object was, and it does fall off like 1/r⁴, right? So okay. Well, thank you.
Right. Yeah.
I have a question for the senior design team. My name is Humberto. I'm from East LA College, and this is my second virtual room presentation, so I'm just stoked to be in this one. We actually have a RoboSub team at ELAC, but I'm not sure how much of the influence that the movie Spare Parts take shape into your design, or if you guys haven't even watched the movie. But in the movie, they talk about cost being one of those variables that actually helped the team win the competition. So when you guys are designing this thing, are you guys looking at cost, or are you just trying to, you know, make the submarine find the objects, or try to get the submarine to, you know, pinpoint that golf ball into that bucket? So did you guys watch the movie and take any lessons learned from the movie? And if you did, what were those changes in your design?
Joseph, do you want to take it or should I?
You can go ahead.
Okay, well, personally, I haven't seen the movie. Joseph and I co-led the team this year, or co-led this team this year. So I'm not sure if you've seen it. Joseph, have you seen it?
No, I know what it is, but I've never seen it.
Yeah, I similarly, I know about the movie. I know what it's about, but I haven't seen it. And as for cost playing a role in our design, we do take into consideration cost because our team comparatively has a very low budget. There are teams that we've talked to at competition who spend like $100,000 on sensors alone, and obviously we have no budget for that. So we are very careful when it comes to our budget, but what we've learned from being on the team is that you can do a lot with cheap sensors if you're willing to put in the work to make them, you know, function the same way. When you're paying a lot of money for different sensors specifically, what you're paying for is the ease of access mostly, because if you buy a prepackaged sensor, it works exactly how you want it to, and if you buy a cheaper sensor, you're more than likely going to be able to do some kind of processing to make it work the same way. So our team has put in a lot of work to get our sensors and our signal processing to work the way that we want it to. And as for raw materials, Joseph, you can weigh in there if you want to.
Yeah, so just piggybacking on that, another big thing that we do is we reuse any components that we can. So things like connectors, we say design like our connector plate to match the connectors that we already have. So rather than trying to design in something new that we have to buy, we'll design to what we already have from previous years. So anything that we can reuse from raw materials, sensors, connectors, components, we definitely reuse. And so that helps cut down costs a lot.
And Joseph, Cedra, what are the rankings like for Cal State LA's team? What have the rankings been these past few years?
Yeah, last year we actually placed 31st out of 50, which is, I think, the best we've ever placed. So we're excited about that. But in past years, we've had issues with various parts of the project because different aspects of like team leadership have been lacking. So this year we've been really focusing on bringing the team together and also having much better organization and all aspects of the project. So this year, unfortunately, like we got pushed back because of the whole virus situation, but this was going to be the year that we like had a really solid chance. So hopefully we still get to go.
Yeah, for your information, that Solar Eagle 3 team at Cal State LA, it took Dr. Raymond Landis about 10 years to finally get that team to be ranked #1.
Yeah.
So you guys are just setting up the foundation for the team. So kudos to you guys. I just love anything with water. I have a background in water resources. So when you guys do all this stuff, and you guys mentioned torpedoes, my son got all perked up. He heard torpedoes. So it's a fun project for students to get involved in. So I'm just happy you guys are involved in this. So good job, guys.
Thank you. Definitely. Thank you.
Sidra, how much of the signal processing was done by the computer science team compared to by your team?
So all of the signal processing was done by the electrical team for the components that have been discussed in our presentation.
Oh, okay.
As far as computer vision, that's handled completely by our computer science team. But for the hydrophones, I did all the signal processing for the hydrophone system, and Arnold took care of the signal processing for the sonar system.
Okay, thank you.
Yeah, great. Really cool work. I loved all the analysis.
Thank you.
I don't know if I've ever seen someone get through 50 slides in 23 minutes or whatever you guys did, so that was pretty impressive too. But I was kind of curious, is there some optimization to be had in terms of the dynamics of the submarine? It seems like maybe it's just the competition, but there's no reason to like reduce the drag shape or reduce the, rotational inertia or the mass of the system. Is there a reason for that, or is that just where you are in the development phase?
That's a really good question. I think in terms of sort of like trying to reduce drag and things like that, not that there's no value in doing that, but if you look up the video of the competition, you'll get a sense of why we don't focus our efforts on that, because you'll see subs traveling at like, I don't know, 0.0001 meters per second. Like it's very slow. So even though there's like these big thrusters on them, you know, the speed is very low, and it needs to be low for the computer vision to work. So if the sub is moving around fast, the object detection doesn't work. And so like when you're attending the competition, you're like, wow, like this is not as exciting as you would have thought, because like we're not racing or anything like that. There's a time limit in terms of how long your run can take, but it's actually a relatively long time limit. It's like plenty of time. So yeah, like the speed is just so low that we never even really take drag into account.
Totally makes sense. That's cool.
One question I have is, okay, first of all, this is good work, and but again, the optimization.
I'm in your optimization class.
Optimization. Yeah, optimization. You guys showed kind of a big factor of safety. I saw the number. It was a quite big number. Why you guys just stop there? Can you further optimize? Can you further proceed?
It's a good question. We are sort of just trying to design for the intent of this thing lasting as long as possible, because we always want like the next year to have a vehicle available to them. So we design with a high factor of safety, trying to keep in mind that tons of new people work on the vehicle all the time, and like I guess like an inherent like characteristic of students is that they break things. And so like we figured if we design it with high factor of safety, maybe this vehicle can live on past just our generation.
Okay, good.
Ramon Flores, you've got your hand up. Do you have a question?
Hi, good afternoon, everybody. More comments, actually. Congratulations to the team. I'm an engineer with the Navy in Port Hueneme. Dr. Tefenchen has been kind enough to invite us many, many times to speak to your freshman class, to visit some of your students. And I'm really impressed, not just by the work, but the fact that it's multidisciplinary. Again, in quote unquote, the real world in industry, everything you do will be interdisciplinary. So I'm glad to see the mechanicals, the electricals and whatnot. So kudos to that. I saw some of the comments earlier from Ms. Tanner down in San Diego. Yes, this team has come a long way. I think I've seen this project for the last 3 years or so. Again, congratulations to Dr. Trujestian for getting another sonar grant. And the last thing I will say, because again, some of my counterparts from the Navy are online, we're hiring. So all you graduating seniors, get a hold of Dr. Trufetian, send him your resume so he can send them to us, and we'll make sure to disperse them and give you guys widest distribution. Maybe it is hiring. Thank you for your time.
Thank you so much. We'll definitely take you up on that.
Okay. I'm sure T. Fox will be reaching out to you as well. So, are there any other questions? All right, if not, well, congratulations, team. You guys did a great job today. This actually concludes our electrical and mechanical engineering presentations for the day. I think that there are some other presentations in other departments later this afternoon, and then we'll pick up again tomorrow. Okay. Well, thank you very much.
Thank you, everyone.
Thank you, Professor. And thank you, everyone, for coming.
I'd like to mention that we have a part 2 of Senior Design Expo for the CS team. So make sure to attend that.
Yeah, so actually our computer science RoboSub team is going to be presenting in the Computer Science Senior Design Expo. So if you're interested in the software aspect of this project, make sure to attend their presentation as well.
Do you happen to know when that presentation is off the top of your head?
I don't. It should be on the website.
I'm going to look it up.
So they haven't canceled it yet, huh? That's good news.
Yeah, they haven't, but they did cancel RoboBoat, which was set to take place in June, I think. Okay. Or no, they postponed it, so they might modify ours, but I guess we'll find out.
Yeah, hopefully they at least postpone it and do something in person. All the essay stuff just got whacked. It was so sad.
Right. Heard, yeah.
So hopefully it doesn't happen to you guys.
Are
Yeah.
they doing like an online kind of judging thing?
Yeah, for the static events, they put those online.
Yeah,
Okay.
I think that's what they're doing for RoboNation's other competitions right now. So
For everybody's interest, the computer science RoboSub is tomorrow at 3 p.m. You'll find the link in the same place you found the link for this meeting. So, okay.
cool. Thank you guys.
Awesome.
Everybody.
Thank you guys.
Did Ha convince any of you guys to stay, Joseph?
Yes.
You specifically, or Sidra, or?
The email from T-Fox was motivating.
I was suggesting grad school. I mean, you guys.
Oh, grad school. Yeah. I'm
I
definitely considering it.
Gotcha. I mean, I think you guys could probably go a lot of places.
Yeah, I actually got accepted to University of Maryland for a EE PhD, so that's where I'm going. Yeah.
That's exciting. Is your mom works for ESPN, right? So is she going back to Connecticut too?
No, not yet. I mean, maybe eventually, but right now.
ESPN's got to be hurting though, right? I imagine.
Yeah, I mean, they're trying to scrape by, but yeah, I know Disney just laid a bunch of people off temporarily, so my mom wasn't one of them, but
ESPN's owned by Disney. I actually didn't know that.
Oh, now you know.
Oh, okay, interesting.
Yeah.
Right. But so Joseph, you're still looking for grad school programs potentially and stuff?
Yeah, I mean,
or work too.
My plan is kind of like to work and do a master's at the same time.
Okay.
I'm kind of like in the middle of a few different interview processes with different places, and then I applied to Cal State LA and Cal Poly.